Good morning, my friends. Sorry I can't be with you today. I have a meeting at the district office. I will be back on Monday, though. So I thought I would take you through some stuff to kind of help us learn more about the ideal gas law, as well as possibly some Dalton's partial pressures as well. Let's get started. Oh, by the way, your homework tonight, let's go over that real quick, will be problems, so chapter 5, problems 57, 59, and 61. So that's chapter 5, 57, 59, 61, and it has to do with this ideal gas law stuff we'll be talking about today. All right, well, let's get started. So we're going to be talking about how the ideal gas law relates to volumes or to gases when we make a change in the gases. So far, our equation that we have so far, PV equals nRT, basically that allows us to calculate any one of these three things or one of these four things if we know three of them. So if we know volume, moles, and temperature, we can calculate pressure. If we know pressure, moles, and temperature, we can calculate volume. But the question now is, what if we have a gas? Say here we have a bunch of dots, we have a bunch of gas in here, right? And then we do something to that gas. We change its volume or its pressure, and now we have this after gas, right? So here, I don't see anywhere in our equation over here that has anything about before or after. So let's take a look. We do know that this equation is true before and it's true after, as long as the gas is behaving in an ideal way. So over here I can say that, hey, PV equals nRT for this gas. And the gas afterwards, whatever we do to it, change the moles, change the temperature, change the pressure, change the volume, whatever we do to it, this equation is still true. Now I do need to distinguish between these two equations. So let's call the before 1. So this is the pressure 1, volume 1, moles 1, temperature 1. Right? So this is all of our starting conditions. And notice R doesn't get a number because R is always the same. There's no R1 and R2, it doesn't change. And over here we are at a new pressure, so we'll call that pressure 2, and we'll call this volume 2 because it's a new volume. And perhaps we have a new moles of gas, so that's N2 and T2. So this is our after situation. We call them all 2's. Again, R doesn't get a number because it stays constant no matter what. So the only thing that relates these two equations is this R that's constant. So what I'm going to do is I'm going to solve both of these equations for R. So to solve for R here, I'm going to divide by N1 T1, and we're going to divide by N1 T1 on both sides. And over here I'm going to do the same thing, but I'm going to divide by N2 T2. N2 T2, N2 T2. And of course N1, N1 cancel, T1, T1 cancels. The same way with the N2 and T2, they cancel each other. And we're left with here is P1, V1 is over N1, T1 is equal to R. And on this side, I'm just going to flip it around. I'm going to say this R is equal to P2, V2 over N2, T2. Notice how these equations have the exact same form, and they're both equal to R, and these R's are equal to each other, which means this has to be equal to that. So we end up with this final equation, P1, V1 is equal to N1, T1. Sorry, not equal to, but P1, V1 divided by N1, T1 is equal to P2, V2 over N2, T2. And we get this really cool result now. Now we have one equation that tells us a before, the 1's are all befores, and the 2's are all after. It's kind of like that M1, V1 equals M2, V2 equation. Is a before and after, or a strong and weak. This is our before gas, and this is our after gas. All right, so this is our equation for changes. We only use this equation, this when something changes about the gas. So if we have a change in volume, or change in pressure, change in moles, or change in temperature, we use this equation. If there are no changes, this is the use when there are no changes. So this is a, hey, I want to know how many moles of gas I have. I know the temperature, volume, and pressure. I can find the number of moles. Nothing changed. I just needed to find something about the gas. All right, awesome. Let's practice using this now. If you need to pause the video now, pause it and finish up. All right, so we have this problem here. We have a sealed container. Starts out at 27 degrees Celsius. We heat it to 127. So this is going to be T1. This is going to be T2. This is the temperature after. So we see right away that we have a change in something, so we're going to use that equation we just developed. And then we crush it down from 35 liters, so this is V1, and to 5 liters, and this is V2. Right? And then we say if the starting pressure was here, so this is the starting pressure, so this is P1. And we're looking for P2. What is that? So let's take a look at how this works. So I'm going to write down my equation. I know P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Now let's evaluate what we know and don't know, right? So we know P1. It's right here, 6.75 atmospheres. We know V1. We know T1. So good. We're good on all three of those. We don't know N1 though. So that's interesting. We'll figure that one out. We don't know P2, but that's okay because that's what we're looking for. We don't know, or we do know V2, sorry, V2 is right here. And we do know T2, but we don't know N2. So N1 and N2 are unknown to us, and that's a problem. But P2 is unknown, and that's okay because we're looking for it. Now if we look up here, we can get some information. A sealed container. This tells us that the number of moles, N, is equal to a constant. So we didn't change the number of moles of gas, which means that N1 is equal to N2. So in essence, this really isn't an N2, it's an N1. It didn't change. And we can tell now that N1 and N1, because they're the same in the equation, these two are going to cancel each other. Because I can multiply both sides by N1, N1, and cancel, 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 cancel. So really my equation is P1 V1 over T1 is equal to P2 V2 over T2. Anything that stays the same will cancel out. And that's true for not only moles, but also temperature or volume or pressure. If something stays constant in one of these equations, they just cancel each other off of the equation. So at this point, I can simply solve here for P2. To do that, I'm going to multiply by T2, so I can cancel that T2, or that T2, and then I'm going to divide by V2, so I can cancel that V2. And whatever I do here, I do over here, so I'm going to put a T2 here and a V2 here. And I see that T2 cancels T2, V2 cancels V2, and I'm left with P2 is equal to T2. I'm going to reorganize it a little bit. I'm going to put the P at the end here. V1, P1. So those three things on top, I've just reorganized them so we can see something later on. And then here I'm going to reorganize this one. I'm going to say T1, V2, and that's going to be my answer. So let's plug in some numbers here. So T2 is 127, and we convert that to Kelvin. It's 400 degrees Kelvin times V1, which is 35.0 liters. And all of that is times P1, which is 6.75 atmospheres. And that is all divided by our good friend T1, which is 300 degrees Kelvin, and 5.00 liters is our good friend V2. Awesome. So in the end, we end up with a value of, let me do all that math, 63.0 atmospheres. And that's how we use this equation. So things that are the same, we cancel them out in the equation, and then we solve for the thing that we're looking for. Now, there's another way of approaching this. We can look at the effects of temperature and volume independent of each other and say, okay, so my temperature went from 300 degrees Kelvin to 400 degrees Kelvin, an increase in 1 1/3 times. And that should also, so if you increase the temperature by 1 1/3 times, that should increase the pressure by that much. So I can do 1 1/3 times the pressure. And this one had a 7-time reduction in the volume, which should be a 7-time reduction or increase in the pressure. So I can do my pressure times 1/3 for temperature, 7 for volume, and I'm going to get that same 63.0 atmosphere answer that I got down here. And that's really all that's happening here. This part of the fraction reduces down to 1 1/3. This reduces down to 7. This is the temperature and volume component, and then times the pressure. All right, pretty cool stuff. I think so. All right, let's try one more example. If you need to pause here. So as we look at this problem, we have 27.0 moles of oxygen. Sorry about that. We have 27.8 moles of oxygen in a rigid steel container at a temperature of 25 degrees Celsius. And we want to add 13.5 moles of oxygen while keeping the pressure constant. So let's label some stuff here. So 27.0 moles of oxygen, that's our N1, it's our starting number of moles. At a temperature of 25 degrees Celsius, this is our T1, our starting temperature. In the end, we need to add 13.5 moles. Now notice we say add 13.5 moles, so this isn't N2. This is what we're going to add. We need to put these two numbers together to get N2, right? So this is related to N2 somehow. We'll do that in a second. Well, let's do that now, actually. So N2 is equal to 27.8 moles plus 13.5 moles. So N2 is equal to 41.3. That took too long, sorry. 41.3 moles of gas. Okay? N1 is this one, N2 is this one, T1 is this one, and we need to find out what should the final temperature be. So we're looking for T2, the final temperature. All right, so let's set this up. P1V1 over N1T1 is equal to P2V2 over N2T2. Now, we don't know P1, so that's interesting. We don't know V1. We do know N1, and we do know T1. Awesome. And this one, we don't know P2, we don't know V2, we do know N2, and we're looking for T2. So in this case, we have this weird conundrum of not knowing a bunch of stuff. But there are some clues up here. Rigid steel cylinder. That means my volume is going to be constant. Volume is constant. Because if it's rigid steel cylinder, it's not going to get bigger or smaller. And then we also see here that the pressure has to stay constant. So those are two things that we need to know. So we know here that V1 is equal to V2, and that P1 is equal to P2. And we know that whenever these things are constant, they cancel each other. Boom, 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 boom. Those all cancel out. Now, some people make the mistake now of just saying N1 T1 is equal to N2 T2, but it's actually 1 over this. So really my thing is 1 over N1 T1 is equal to 1 over N2 T2. And here I want to solve for T2. I think the easiest way to do this is going to be to cross multiply and divide. So I'll take that one, and I'll say N2 T2 is equal to N1 T1, which in the end we get the same result as flipping earlier, but there it is. And then we want T2. N1 T1 over N2. And then that is equal to 27.8 moles times 298 degrees Kelvin divided by this 41.3 moles. And that ends up giving us, I haven't done the math yet, 27.8 divided by 41.3, 0.6. That's right. And then times, 298 ends up giving us a temperature of 201 degrees Kelvin. So if we want to add more gas to a container but keep the pressure constant, well, geez, we're going to have to cool it off significantly. And that's what this means. So that's how to work with this equation. The key thing here is that when things are constant, you just cancel them. Yeah, pretty straightforward. So your homework again tonight, my friends, is Chapter 5, problems 57, 59, and 61. Hey, and a word of warning that we will have a test over Chapter 5 on Tuesday. We'll do one small new thing. We'll do Dalton's partial pressure. Dalton's law on Monday. Read about it in Chapter 5. You know what? Let's just give that assignment to you, actually. I was going to hold off on that, but I think it's wise to knock it out. Let me make sure what section it is. So that's section 5.5. So do an SQ3R or whatever note thing you like to do. SQ3R and add to that 5.79. So another question here is 79. Awesome. That's it for today, my friends. If you want to get started on this work, I'll try to have access to some books for you. And have a great weekend. Work hard, learn a lot, and be safe out there.